What do you think? When will the era of technological singularity come? Maybe it's already on the threshold. Or are we, without realizing it right now, already living in that very future? From science fiction movies? These questions have a real basis. After all, it's coming very soon. James Webb and other telescopes that are planned to be launched into orbit in the near future may detect signs not only of biosignatures, but also technosignatures on potentially habitable planets. What does this mean in plain language? This means that modern telescopes are not just capable of monitoring the universe and finding large star systems and galaxies, but they can also see smaller structures. They are able to detect even technosignatures, meaning the light from alien megacities or technological structures, if those happen to fall within their field of view. That's why nothing prevents us from searching for such signs. For example, in the Proxima Centauri system, you may think it's science fiction, but it's not. This is already possible thanks to the latest equipment that James Webb is equipped with. In particular, it's worth paying attention to the mid-infrared instrument spectrograph. It's the one that, through the veil of light years, can detect artificial light on planets orbiting distant stars. What would such a discovery mean if it happens? Detecting technosignatures would show us that a civilization with technological achievements dominates that celestial body. Previously, Earth's equipment was not capable of detecting such signs. So this is a significant leap, promising us a whole range of discovery opportunities in the near future. But James Webb's activity is just the beginning, so to speak, the trigger for progress. In a few years, the Astronomical Observatory Extremely Large Telescope, the Extremely Large Telescope, will be launched, which will see farther and more thanks to its nearly 40-meter mirror made up of 798 segments. This multi-billion euro project promises to make a breakthrough in our understanding of the universe. Its unique adaptive optical system is capable of an extremely high level of detail that no ground-based telescope has achieved so far. Right now, our astronomers are like inexperienced first graders who are just beginning to learn the basics of science, timidly lifting the veil on the mysteries of the macrocosm. Why are scientists placing their hopes specifically on the Extremely Large Telescope? In addition to being packed with high-tech equipment, its eyepieces can see 100 million times more than the naked eye, and 13 times more than any of the modern large telescopes. Standing in the middle of the Atacama Desert, 130 kilometers from the nearest settlement, at an altitude of more than 3 kilometers above sea level, the Extremely Large Telescope will be able to find traces of plants and other signs of life on the surfaces of planets that we can't even see. It is equipped with next-generation spectrographs and cameras that will literally pierce through time, as they will be able to track the distribution of matter in the universe starting from the moment of the Big Bang. Is that even possible? After all, just a few years ago, scientists were excited about any blurry image of a distant star or an almost invisible dot of a planet passing across the disk of that star. And now, you don't even have to wait for the launch of an extremely large telescope. James Webb himself is capable of detecting sources of artificial light coming, for example, from alien cities located in the Proxima Centauri system or any other location at that distance. An interesting fact, James Webb Space Telescope can also monitor signatures on Earth. By closely examining megacities like New York, Tokyo, Buenos Aires, or Hong Kong, you can't even imagine how powerful a scientific and technological breakthrough this is. Just think about it. James Webb, for the first time among the family of telescopes, is capable of filtering out both natural and artificial light. Of course, if this parameter can be detected and classified on the surface of the Earth, then it's quite possible to do the same when observing Proxima-b. What can such monitoring provide to Earth scientists thanks to the data obtained by James Webb and other telescopes after him? When technosignatures are detected, meaning traces of artificial lighting on other planets, conclusions can be drawn about the technological achievements of distant civilizations, their scale, and types of mechanization. This is another step toward achieving technological singularity, or rather, its threshold. Humanity will enter this state when it launches the first functional quantum computer at this point to the same Proxima Centauri. If we decided to contact its inhabitants after discovering technosignatures on one of the planets in the habitable zone, the message would take about 4 years to travel one way. But with a quantum computer, it would be possible to contact any point in the universe, literally, in real time. Right now, a full-fledged quantum computer is an anesthetic device. But there was a time when even a car was considered something fantastic. You don't have to look far. Back in 2016, the capabilities of James Webb were discussed as something incredible. In particular, scientists were amazed at how exactly the telescope would study the surfaces of exoplanets and how detailed this process would be. Now, in 2024, this incredible future has arrived. But, to be fair, it should be noted that the eyepieces of relatively primitive telescopes, even back then many years ago, were already aimed at Proxima-b as the closest exoplanet to us, where life could potentially exist in some form. Thus, with the capabilities of James Webb and the telescopes that will be launched in the future, the study of this planet's surface, as well as its orbit, will become one of the priority areas of activity for orbital and ground-based observatories. Why was Proxima-b chosen as the target for study and monitoring? Is it really just because it is located relatively close to the solar system? Is that the obvious reason? But if you look deeper into the question, it becomes clear that Proxima-b is located in the Goldilocks zone, that is, the habitable sector of its star, Proxima Centauri. That means life could very well have developed there. The planet was discovered in the summer of 2016 using the radial velocity method, which is based on observing the spectral lines of the star. The distance from Proxima-b to its star is just over 7 million kilometers. But since the red dwarf has low luminosity, the celestial body receives just the right amount of energy and heat to keep water in liquid form on its surface. Up to this point, we don't know if this planet is habitable. There are concerns about the frequent high-energy radiation attacks on Proxima-b from its parent star. This level is 60 times higher than on Earth, and the amount of X-ray radiation penetrating the planet is 400 times greater than on Earth. And this is considering that Proxima-b has no magnetic field of its own, which means it is completely defenseless against its star. But could this really be an obstacle to the development of life, provided that a highly technological civilization exists on the surface? For example, on Earth, people protect themselves from excessive ultraviolet radiation with biological fluorescence, so nothing stops the highly developed inhabitants of the planet from inventing something similar. However, 7 years ago, Earth equipment recorded a series of powerful flares on Proxima Centauri. If there was life on the planet, such an event could have completely sterilized the celestial body. It's also important whether Proxima-b has an atmosphere. Why are we being asked this question? Since the planet is tidally locked to its star, one side is in eternal night while the other is in constant daylight. If there is no atmosphere, then life as we know it would be impossible on the planet, because one side would be a scorching desert and the other an icy wasteland. An atmosphere, on the other hand, would distribute heat more evenly, making the surface of Proxima-b less lifeless and extreme. But this is just speculation. Only James Webb and its successors can fully dispel all our doubts. He was the one who ushered in a new era of exoplanet research, literally examining them under a magnifying glass. By the way, the telescope has already managed to detect biosignatures on one of the distant planets called K218b. Among the components of biosignatures, the most important is ozone as a marker of possible life on the planet's surface. Ozone appears as a result of biological processes occurring on the celestial body. However, when it comes to the planet K218b, apart from biosignatures, which are present in rather modest amounts. Nothing else has been discovered so far. There haven't been any, not even artificial light. But let's think about it. Are those the only signs of an intelligent civilization? After all, K218b could turn out to be an ocean planet, with its megacities bustling beneath kilometers of water. That's exactly why we don't see any light background emitted by them. Besides, James Webb's goal is to detect life in general, even if it's just at the level of bacteria or plants. That would still be an amazing discovery, especially considering the centuries-long silence of the universe. Despite our persistent search for any signs of life beyond Earth. But is James Webb capable of detecting barely noticeable traces of life at such enormous distances? We can say with confidence that yes, it can. And it's all thanks to the hardware of this unique telescope. For example, it is equipped with a fine guidance sensor, which allows it to capture images of the highest quality, as well as a number of spectrographs that operate in the infrared range. Again, the previously mentioned MIRI is capable of seeing not only bio and technosignatures, but also the redshift of extremely distant galaxies, barely visible comets streaking through space, and even the tiniest objects in the Kuiper Belt. But even the capabilities of James Webb, the pioneer of a new level in the search for extraterrestrial life, may eventually seem insignificant. For example, the successor to James Webb Space Telescope is LVA, a revolutionary next-generation telescope. Its extremely high angular resolution will allow it to easily find habitable worlds by closely monitoring their atmospheres. This telescope is also planned to be launched into Earth's orbit so that nothing interferes with its operation. In any case, each of the existing telescopes or those planned for launch in the future, James Webb Space, Telescope Extremely Large, Telescope LVA, will make a significant contribution to the study of the universe and the search for life in its vast expanses. Some observatories will focus on more distant worlds and galaxies, while others will study what is literally right under our noses. Here, for example, is what the cloud of hot gas surrounding the black hole in the Perseus galaxy cluster sounds like. In any case, we live in an amazing time when with each passing year, our familiar picture of the world and its boundaries will continue to expand. Where will these discoveries lead humanity? Could the search for extraterrestrial life become the beginning of the end for our civilization? Try to answer these questions in the comments. When we talk about space telescopes, the first ones that probably come to your mind are Hubble and James Webb. But do you know anything about the telescope? Chandra is a space observatory that began its work on July 23, 1999, which means that in 2024, Chandra celebrates its 25th anniversary. And in honor of this, National Aeronautics and Space Administration has shared with us many images of objects that Chandra has studied over this period of time. So we invite you to take a closer look at these truly fantastic images. From supernova remnants to star-forming regions, what cosmic mysteries has Chandra revealed to us? Here, you see the Crab Nebula, which consists of fragments left after a bright supernova explosion. At the core of the nebula is a pulsar, which appears in the image as a bright white dot surrounded by a purple cloud. You have to admit the Crab Nebula looks a lot like a mushroom. We also present to you an image of the nebula from other telescopes, an image of the nebula and Hubble. Let's move on to the nebula. Orion is one of the closest star-forming regions to our planet. Just look at this scattering of pink and white stars. Here, we see a flash of a red cloud that stands out noticeably against the general background. And as a bonus for you, here's the Orion Nebula. In the infrared range from Hubble, the galactic eyes New General Catalog 4438 and 4435. In the lens of Chandra, we see a distinct purple cloud near the galaxy New General Catalog 4438. Its sister, New General Catalog 4435, is located in the central part of the white stripe and is also surrounded by a purple ring. But here we see a completely different picture through the eyes of the European Southern Observatory telescope. Chandra allows us to look at many cosmic objects from a completely different angle. In the Milky Way galaxy, there is a rather unusual nebula called the cat's paw. Take a closer look. It really does resemble a cat's paw. We see a cluster of neon purple and white stars. Chandra showed us numerous young stars. You can also look at this unusual nebula thanks to the European Southern Observatory Max Planck Gesellschaft and Spitzer telescopes. Now let's take a closer look at the galactic center of the Milky Way. This area is quite difficult to study because there is a huge concentration of dust and gas. However, Chandra's X-rays were able to penetrate inside. In the images, we see clouds of hot gas. You see the bright spot in the lower right corner? That's another star-forming region. Sagittarius C has spread its wings wide. The Eagle Nebula? You might know it from the famous image provided by Hubble. Chandra showed us the glow of young stars, a faint misty radiance and dust clusters. And now it's the turn of the Bat Nebula itself. The nebula is actually a reflection of the disk of a young star. Batman could use the Bat Nebula as his symbol. Subtitles created by Dimatorzok. Let's take a closer look at the Spiral Galaxy New General Catalog 7469. Its special feature is that you can actually see a black hole in it. In Chandra's X-rays, this object looks like this. This purple dot is X-ray emission from the hot gas that has accumulated around the black hole. This is how the galaxy looks through the lenses of Webb and Hubble. Next up, we have another black hole located in the central part of Centaurus. A streams emanate from it, turning into a scattering of stars. In the images, you can notice a translucent blue sphere, which was also formed under the influence of the black hole. And here is a cluster of galaxies in the Virgo constellation. In the images provided by the Chandra Space Observatory, we see numerous galaxies as white dots and some with glowing rings. We see a neon purple stripe. This is a cluster of hot gas. Here's how the galaxy cluster looks in images from other instruments. This is the bright massive star Wolf-Rayet 124. The pale pink hue and the glow from the star at the center make the object look very much like a butterfly spreading its wings in flight. In the image taken using X-ray radiation, we can observe many stars surrounding Wolf-Rayet 124. Here's how other research instruments have shown Wolf-Rayet 124. This is a nebula formed from the remnants of the supernova G21509. In fact, these are fragments of a star that broke apart due to the supernova explosion. The nebula is surrounded by X-rays. And here is the cluster that remains after the star explosion. This expanding sphere of matter and energy is the supernova Cassiopeia A. In X-ray radiation, we can see the shock waves. New General Catalog 3532, which is also called the wishing well, this is a cluster of stars about 300 million years old. The stars here are completely different. Some are larger and some are tiny, orange, violet, golden, yellow, and white. New General Catalog. 6872 is a spiral galaxy that is connected to a smaller galaxy. The latter most likely has a black hole inside it, which is taking gas from New General Catalog 6872. Once the astronomer Edwin Hubble discovered the beautiful planetary nebula HB5, which represents the final phase of a sun-like star. Chandra captured the X-ray emission of the object. Here is Hubble's image of HB Yites. There is also a rather unusual radio image from Atacama Large Millimeter Submillimeter Array. This is an outflow from a yellow-colored star, which is carbon monoxide. Now get ready to see Jupiter in an unusual form. We can notice purple spots. This is X-ray aurora, which occurs as a result of atmospheric gases colliding with high-energy particles, as well as X-rays detected by the Chandra telescope. If you look closely, you'll see a blue ring around the planet in the images. The great variety of cosmic objects of all fantastic shapes and sizes. This is all part of our reality in the vast expanses of our universe. Such nebulae and clusters of galaxies seem to have come to us from science fiction. And thanks to the Chandra telescope, we were able to see this. News from the vastness of space continues to arrive. For example, did you know that a mysterious comet called C2023 A3 key Chi-Jinshan Atlas is heading toward us? What makes this object so special? First of all, it's worth mentioning that we observe comets in our night sky extremely rarely, although the last one appeared relatively recently in 2020 called C. 2020 F3 Neowise. However, our comet will be much brighter, and it will be clearly visible from the northern hemisphere. C. 2023 A3 Chi-Jinshan Atlas. It will also be so noticeable because it will have a long, truly magnificent tail. This nucleus will melt as it approaches the sun. How I wish I could see this amazing sight with my own eyes. You've probably noticed that the comet has a very long name, and that's not just for show, Atlas, because a telescope with that name first detected this object. That was in February 2023, quite recently. Atlas is located in South America. One of its features is the early detection of objects that could collide with Earth, mostly asteroids. At that time, it was still unclear whether the telescope had discovered a comet. It was still uncertain. However, it was determined that the object was located approximately between Saturn and Jupiter. Later, scientists found out that the comet had actually been observed before, specifically in January 2023 at the Chinese observatory Chi-Jinshan. That's where the name Chi-Jinshan came from. In the name, A3 also indicates when the comet was discovered, and that's the first half of January. A3 tells us that it's the third half, an object like this found during this period. The letter C indicates that the comet is non-periodic, meaning it passes through the solar system only once, or a very long time must pass before it returns again. Since its discovery, the comet has come under the close scrutiny of scientists. Initially, its speed was approximately 80 kilometers per second, and it was too far from our planet. Now the comet is much closer to us, and the interest in it is only growing. What path has the comet taken all this time? And here we should get acquainted with the concept of stellar magnitude. It indicates the brightness level of an object. The lower the value, the brighter the object. In August of this year, Comet A3 had a magnitude of 6 and was in the zone of invisibility. By the end of August, its magnitude was 7. When the comet gets close to Venus's orbit, we'll have the opportunity to observe it, but only if we're in the southern hemisphere. Remember, Comet International Scientific Optical Network, or C2012 S1. When it was discovered in September 2012, it was almost immediately dubbed the Comet of the Century. Everyone was eagerly awaiting its approach to the Sun because it was supposed to be especially bright, one of the brightest, if not the brightest comet in cosmic history. Expectations were very high, but unfortunately, everyone was in for a disappointment. On November 28, 2013, the maximum approach of ASON to the Sun occurred. Then, to the great horror of scientists, significant changes in the structure of the comet were recorded due to gravitational and thermal influences. The mass fell rapidly and ASON broke into smaller fragments. It was later found that the nucleus had disintegrated about 3.5 hours before perihelion. As a result, we only got faint remnants of the comet, which were nothing special. And how many hopes there were? It is worth mentioning that the situations with Comet A3 and International Scientific Optical Network are different. The distance between A3 and the Sun at closest approach will be 50 times greater than that of International Scientific Optical Network. So at least in this regard, we can be more at ease. However, this is not the only interesting point. From around October 9 to 12, direct scattering may occur with A3, and then the visible brightness of the comet will increase sharply. During such an event, light passes through the dust, gas is pulled out and returns to where it originated from, and against the background of the Sun's glow, the comet will appear even brighter. From our perspective, it might just blend with the Sun. We can see something similar in the image of Saturn provided to us by Cassini. Because of direct scattering, the fainter outer rings appear more pronounced in this case. Between October 9 and 12, A3 will reach a high level of brightness with a magnitude of -3, all due to direct scattering. And this is a record brightness for comets in history. For example, the well-known comet Hale-Bopp had a maximum magnitude of -1.8, and other comets had even lower values. The theory of the expanding universe is, you could say, the queen of all cosmological theories. It's the foundation of our knowledge about the cosmos. Scientists have spent a lot of effort and time to finally arrive at this knowledge. However, like a bolt from the blue, data appeared that loudly claims that in fact there is no expansion happening in the universe. It is simply motionless and flat, just as Einstein once supposed. But does this mean our understanding of the universe is fundamentally wrong? And what news has the James Webb Telescope brought us? The James Webb Telescope has provided us with data about some cosmic objects that do not fit into standard cosmological theories. For example, it found that extremely distant galaxies go through stages of their evolution at a different pace than others. Let's take the galaxy GNZ11, thanks to James Webb. We found out that there is a black hole inside it. That would be fine, but this black hole is too massive. For a galaxy of that age, meaning in the period after the Big Bang, it simply couldn't have become that huge. And this isn't an isolated case. More and more often, elements have started to be found in other galaxies that also couldn't have formed if we rely on the distance of the galaxy and the generally accepted models of thermonuclear reactions. What is the reason for this? Could it be that the basic theories of cosmology are incorrect? For a long time, galaxies have been studied by Hubble, and he actually confirmed the main theory of evolution in space. Galaxies began to form within 1 billion years after the Big Bang occurred. And now we see that James Webb has provided us with completely opposite data regarding the accuracy of these telescopes' work. There is no doubt. So what is this related to then? Or are we talking about certain white spots, gaps in our theories? To begin with, let's go through all the stages of the formation of the first galaxies. So, roughly speaking, dark matter was responsible for them, specifically its gravitational influence. Because of this, gas began to accumulate in the proto-galaxies, which led to the emergence of the first stars. Since the universe was very small at that time, according to the standard theory, there simply wasn't enough space for all the objects, so many of them began to merge together under the influence of gravity. This led to the fact that the first galaxies didn't have any clear structure. They hardly resembled modern galaxies. They were shapeless and not very large. Remember, the universe was much smaller then. These are the types of objects visible in Hubble images. However, determining their exact age required first establishing the photometric quality, which couldn't be done immediately. Redshift, what does it mean? In a universe that is constantly expanding, all objects are moving away from the Milky Way, except for those that are gravitationally bound to it. If a galaxy has moved farther away, the redshift becomes greater. This method cannot be applied to low-mass galaxies because we cannot obtain their spectra. Here we have to use another method, looking at the fluxes of radiation through several different filters. And it turned out that the galaxies we are studying have moved quite far away from us. The shift was so strong that Hubble perceived the visible light coming from them as ultraviolet. Hubble's capabilities in this case were not unlimited, so there was a need to launch a more advanced device that would be sensitive to the infrared range. As we already mentioned, James Webb provided us with data. We were able to observe the galaxy along with those elements whose light was absorbed by interstellar dust in Hubble's images. As a result, we obtained clearer images, making the galaxy more distinct and its shape easier to understand. We can notice this if we compare images of the same objects taken by the two telescopes. The difference is obvious, isn't it? Thanks to James Webb, we found out that spiral galaxies actually predominate in the universe. They make up as many as 42% of the total. Irregular galaxies come in second place, followed by elliptical and other types. So we now know for sure that there are far more spiral galaxies in the universe than was originally thought. And here, one contradictory fact emerges. As we move away from the Milky Way within systems whose stellar mass exceeds 1 billion, the proportions of galaxy types hardly change, and this again contradicts the established ideas about galaxy formation. For now, we have two possible explanations. Either structures form much faster than we previously thought, or, in most cases, collisions between galaxies have little to no consequences. But can this really be explained that way? That's a question we still have yet to answer. Add to this the fact that, besides the prevalence of spiral galaxies, the number of regular-shaped galaxies is much higher in the distant regions of the universe. And that's quite an interesting fact, and we also have yet to explain it. Understanding how our universe forms, how galaxies emerge and evolve, is very important because it's the foundation of all cosmic science. Thanks to this knowledge, we can also understand whether it's possible for a planet like Earth to exist in other galaxies. James Webb has given us a lot of food for thought, and we really hope that the picture of the universe will become clearer for us. And what do you think? How soon will we solve this interesting mystery?